Hello, everyone. Happy Wednesday. Great. We're going to get started with our first video, which is our first one on sound functions.
We're now starting our next section on computational sound. We'll be covering a variety of functions to help us complete the third mini-project of this course. In this chapter, we'll be covering how to work with audio within Wolfram Language. We'll be going over the functions sound, sound note, and play, as well as how we can edit and analyze audio objects. To start analyzing audio in Wolfram, we need to have audio to work with. There's three primary modes for this we're going to cover in this chapter, starting with sound and sound note. To create audio with a more musical slant, we can use the function sound note inside of the function sound. We can think of our construction of sound and sound note as somewhat similar to how we need to wrap shapes within the function graphics to get a visual output. In order to get sound, we need to wrap our sound notes inside of the function sound. Sound note can take two different kinds of arguments. We can give sound note a specific named note, like C, and we'll get a sound playing a C. Still working off of musical notes, we can also use numbers within sound note. These numbers correspond to semitones, or half steps on a musical scale, with 0 set as a middle C. So if we want to play the note above a middle C, we could write D within sound note, or we could use the number 2, as one note is 2 half steps up. Similarly to graphics, we can put multiple notes within sound to create a sequence of notes. If you're musically inclined and want to create chords, we can do that by putting multiple note specifications within sound note. Beyond just the notes, we can set how long notes should play by adding an additional argument to sound note. By default, the length is 1 second, but we can set them to play for longer or shorter. We can also play our notes in a variety of styles. You can find a full list on the documentation page for sound note. Just like how colors work within graphics, we put the style within our list of notes, and the style will apply to any sound notes after the style within the list. If we put a new style in the middle of our notes, the style will change for the second half of what we're playing. Another approach to creating sounds within Wolfram Language that is less musically oriented and more mathematically oriented is using the function play. Instead of taking sound notes like sound does, we input waveforms, which are equations dependent on time representing the pitch of the sound, and we put that into the function play. Our first argument is the equation for the waveform, and our second is the variable we're using for the time and the start and end values for that variable. When we give play a list of waveforms, we'll get those two waveforms playing at the same time. We can use sound to string together different waveforms to play in sequence, just like how we can string together sound notes to play in order. We've been using the terms sound and audio somewhat interchangeably in the first part of this chapter, but actually Wolfram has separate and distinct sound objects and audio objects. Sound and play return sound objects, which are useful, but a lot of our editing and analysis functions are suited for audio objects. We can take code that creates a sound object and turn it into an audio object by putting the function audio around it. We'll see that this output visually looks very different from the sound objects we created earlier. If we're not starting with a sound object, there's a few different ways we can get audio objects into our notebook. We can use the function audio capture to get the live audio from a microphone or other input. Another option is to import audio files. In this example, we're tapping into the function example data, which is built into the Wolfram language, to get the audio of a car. Now that we have audio objects instead of sound objects, we can edit them. There are more ways to edit audio than we're going to cover in this chapter, but the essential ones we want to know are audio trim, audio pad, and audio delete. Audio trim lets us trim off audio from the start, end, or both of an audio object. If we don't give audio trim a second argument of a start or end time, or both, it will automatically trim off silence from the start and end of the audio object. Audio pad has a similar syntax to audio trim, but works in reverse, where it will add silence to the start and end of the audio. Audio delete works similarly to audio trim if we give it a start time or an end time, and then it will delete the sound before or after that time. However, if we give audio delete a list of 2 times, It will delete the audio in that time interval and return one audio object with that section missing. The three functions we just covered all return one audio output. If we want to split or analyze our audio in different pieces, we can use the function audioSplit to split the audio at a specific time or times. Another useful function for looking at audio in pieces is the function audioIntervals. AudioIntervals takes in an audio object as the first argument, and the second argument is a test for what intervals to look for. One of the built-in tests for audioIntervals is inaudible, which returns the time intervals when there is no sound, up to a small threshold. This can be useful for removing a chunk of silence in the middle of audio, as you can then use the function audioDelete to remove the intervals that audioIntervals gives you. Along with editing audio, we can dive into the actual numerical information behind it. Some easy starting places for this are audioPlot, which gives us the plot of the waveform for an audio object. The functions spectrogram and periodogram also return plots for audio objects. A spectrogram will show us the time frequency plot, and a periodogram will show us the power spectrum plot. Plots are useful for visualizing audio, but what if we want to get the raw values? Spectrogram array lets us get the actual values behind the spectrogram for an audio object. Another useful function, and one that will be important later when you start working on this section's mini project, is audio local measurements. With audio local measurements, we can take an audio object and get some property for the audio over its duration. For example, RMS amplitude is a type of measure for how loud audio is at a given time. We can get the values within a time series, and then we can plot the output for that property. We've covered a lot of the basics for working with sound and audio in Wolfram Language in this section. While we won't necessarily need it for our mini project, there's a lot more we can do with audio. If you're interested in going further with audio in Wolfram Language, the lesson notes for this chapter has links to some useful guides. But from this chapter, we've now got the skills we'll need to work with audio in this course. You now know how to use sound notes to create audio from notes, and play to create audio from waveforms. You've also seen how we can use functions like audio trim, audio pad, audio delete, and audio split to edit audio, and how we can analyze audio visually or numerically with audio plot, spectrogram, and audio local measurements.
All right, awesome. We're going to move on and do some polls now. I believe we actually have two short polls for this section. Looks like pretty much everybody got it. All of those three are different ways you can visualize an audio object. You just saw audio plot, spectrogram, and periodogram create different visualizations, but still visualize audio for us. All right, awesome. And then we'll move on to the next poll. Most people seem to get this one, but just to reiterate, so sound and audio are different in Wolfram. We've got those audio objects and the sound objects, and they are not the same, but as with it says in answer B, we can easily convert sound into audio using that audio function. All right, awesome. So that's it for the polls for this section, and we're going to move on and work on some exercises. Real quick, if you need that link to the framework, it should be up in that little box you can click over by the chat and stuff. And also just want to reiterate what Robs was saying earlier, that the framework is still kind of in beta. We're still working on it. And it'll be released to everybody in a few weeks. But in the meantime, we ask that you not share the link to the framework outside of the study group. So on community with friends, please don't share it yet. Once the full course is live, you're welcome to share it however much you want, but not quite yet. All right, awesome. So let's look at our exercises for this section. Cool. Before we start, and I can't zoom this part, unfortunately, but I don't believe we've seen it yet on any of these exercise notebooks, but as we get into some more complex stuff, you might see a little bar at the top that says this file contains potentially unsafe dynamic content. It's not unsafe, we promise. You can click Enable Dynamics and everything will work fine. You'll see this when you're working with sound. That's why this little box is grayed out. And also later on as we get into other kind of interactive content. So I'm just going to enable that, and let's do exercise 2. So we want to remove any quote-unquote silence from the audio without using the test inaudible. So we have to make our own test. And we have our little audio sample here. Run it and make sure that's the right definition. Great. And so we kind of just saw how to do this, but we have this function audio intervals where we can give it an audio object and then we give it some kind of test. And in our example, we did inaudible, but we don't want to use that this time. So instead, what we can do is we can construct a pure anonymous function to be our test. So it'll slot in values from the audio. And we're going to do our slot as always. And then after it, we're going to write RMS amplitude. Hopefully I spelt that right. And this is saying, okay, get me this is a specific property of the audio, but it's basically getting how loud that audio is. So it's saying, great, for every time the audio, get how loud it is. And we're going to select it out if it is less than, and we're going to just get a small number. So we're saying if the volume is super duper small, we're going to get those audio intervals out. If we run this, we get a couple different times in our audio where it's silent. And we can then use audio delete and just put in our audio and then take this output here, pop it in, and we'll have our audio with with any points of silence edited out. Awesome. So I think we are now going to move on to our next section in this course. Unless there are any questions, I'll answer that in between the videos.
In this chapter, we're going to be covering scoping constructs. We'll learn how to choose between the three primary scoping constructs you'll see within Wolfram Language: with, module, and block, and how to use them to organize and structure your code. Before we get into coding with scoping constructs, let's talk about what a scoping construct even is. When we're coding, especially as our code and functions get more complex, we may find ourselves wanting to use variables within a piece of code only for that chunk of code and not for our entire notebook. In a similar vein, we may be writing a function with intermediate steps that would be better organized with variables for the different steps. This is when we would want to use a scoping construct. Up to this point, we've been using variables, but they've all been global variables, meaning the definition of those variables is the same everywhere within our notebooks. Scoping constructs create a local environment and let us set local variables, meaning they'll only have a definition in that code where we have a scoping construct. Or, if they're also defined globally, they'll have a different definition in that local environment. The first scoping construct we're going to cover is with. With is the simplest in a sense, but is also the least flexible. To use with, our first argument is our local variables within a list, and the second is the expression we want to run using those local definitions. So we can set x equal to 2 inside of our first argument, and in our second argument, we can write x squared. When we run this, with will use that local definition for x, and the code will be evaluated with 2 squared, and our output will be 4. Since we've used with, if we define x globally as another number, it won't impact the output from with, as the local definition will take precedent over that global definition. We can also list out more local variables if we want by adding them to that list within the first argument. If we were to have a variable defined globally that we don't define locally, with will use that global definition. I mentioned that with isn't as flexible as the other scoping constructs in Wolfram Language. This is because we have to define our local variables before the expression will be evaluated. This means that if we have an undefined variable listed in our first argument, we'll get an error message. This means that if we want to have one local variable dependent on another local variable, we can't use with. If we try that within the first argument, with will reference global values and not local ones for that dependent variable. If we do want to have local variables that are dependent on another local variable, or we want to hold off on defining a variable until later on in our expression, we can use module or block. The syntax is still the same for these functions, and they can do the same operations as with. We can run multiple expressions in order with any of these three functions by adding semicolons between the lines we want to run. Unlike with, Module and block let us leave local variables undefined and then define them later. This lets us have those locally dependent variable definitions. While we still can't have those definitions that are locally dependent within the first argument, what we can do is make those definitions happen later on in the second argument. Just because they're more flexible and can do the same things as width doesn't mean you'd always want to use block or module. Width generally runs faster than those other options. With the scale of computations we're doing in this course, however, evaluation time will likely not be a huge concern. We've now talked about how width is different from module and block, but how are module and block different from each other? On the surface, they're pretty similar, and you could use both for a while without encountering any differences. However, internally, these functions operate different in how they localize variables. Module uses what is considered lexical scoping, while block uses dynamic scoping. In practice, module creates new symbols, while block is looking at the history of variables. As a result, block can reference global variables in an output in a way module will not. This is a bit easier to see with an example. If we set the variable m to globally be equal to I squared, and then we use block to localize I to be equal to a, and then we call that global definition of m, block is able to slot that local definition for I into that global definition for m, because it's looking at the history, and those i's are the same variable from the perspective of block. Module, on the other hand, can't make this substitution because it's internally creating a new variable for I. We can see this new variable and how it's different from the one in our definition of m if we run module without defining I. Unless you have a reason you want block's method for handling local variables with global variables, it can be a good idea to use module as your default, as you're less likely to run into weird outputs from interactions with global definitions. In this chapter, we've gotten a handle on the basics of using scoping constructs. You've seen how we can use block, module, and width to create local environments, and the differences between the three of them. While scoping constructs were not covered as a core concept at the start of the course, as we're getting more complicated in our coding needs, they'll become absolutely essential.
All right, awesome. We've got a couple more polls for this section. So you should be able to see an open poll right now on why are scoping constructs useful? All right, awesome. It looks like most everyone got this one. Scoping constructs are useful because they let us set local variables. So being able to have that local environment to work in is super useful. It does end up being very useful to use scoping constructs when you're creating complex functions, but you don't have to use one. All right, awesome. So then we can close that one. I think, yeah, we have one more poll for this section. All right, cool. Seems we've got a decent number of responses, and almost everybody did pick C, which is that width cannot have local variables that are dependent on another local variable. This is because width requires us to define all of our variables in that very first argument. We can't define them throughout. All right, awesome. I think we're good on polls then for this section. So we'll go and do our exercises. So let me get that, Sharon. Great. Cool. So we're going to do exercise 1 here. So we want to create a list of colors that show a gradient between red and blue using width. Your final list should have at least 5 colors. Cool. So we know we're going to use width. And we know width is going to have something here. And then we're going to have code after that. So first, we're going to want to have red and blue somewhere in here. I'm going to just call those colors. And I'm going to create a little list of them right up here. Great. So I've got my colors, red and blue. I want to do a gradient between the two of them. And one useful function for that is going to be blend. So if I give blend a list of 2 colors, it's going to blend them together 50-50. However, instead of having to do a bunch of nested blends, if we wanted to get a split other than 50-50, we can give it some number between 0 and 1 in our second argument, and we'll blend that amount. So if we give it a really low number, it's going to be mostly towards whatever our first color is, which is red. If we give it a really high number, it's going to be close to our second color, which is blue. So we can use this to be varying our gradient. So we've got width, our color set to these. Let's use table in this case. So we're going to build a table, and we want to blend some, we want to blend two colors. So I'm just going to do color here, and then I want the color. Sorry, I messed that up. I want colors here. So I'm blending red and blue in some capacity, and I want a number in my second one. And then I'm going to change my number. So I know my number's I. I know full red is going to be 0. Full blue is going to be 1. So I know that's my bounds. And then I need to figure out how much I want it to change with each step we do. In this case, we want to have a minimum of 5 colors. So we need this to at least be a fourth, or 0.25. If I run this, I get a nice, lovely little gradient. If I wanted to, I could make this a smaller step size so there's more. I could make it just be 0.5, and then we would just have just that middle color to make our little gradient width. Awesome. And in this case, if you're working on these exercises, in this case, we maybe didn't really need to use width, but width is useful then for the second exercise in this one, which you guys can do on your own time, which is building off of this first code. All right, awesome. I believe that's all of the exercises for this section, so we can move on to our next video.
We're now on to the final material before our third mini project. In this chapter, we're going to be discussing some of the basics for data analysis in Wolfram Language. We'll cover how to import data into our notebooks, how to work with time series, and also just scratch the surface of built-in functions to help with statistics and fitted models. Before we can analyze data, we need to get data into our notebook. There's a few different ways to do this, and it'll depend on the form of your data or where you're getting it from. Sometimes, like we'll see in our mini project, our data is in some kind of output from a larger computation. In that case, it's already in our notebook to work with. However, for external data, most commonly you'll use the function import that can import multiple different file types into our notebook. The formatting of that imported file will change depending on the original format. For example, if we import a CSV, we'll end up with a list of lists for the rows and columns within that file. One great resource for finding and importing data into notebooks is the Wolfram Data Repository, where users can contribute formatted data sets for easy use within a Wolfram notebook. We can get the data itself using the function resource data. This example imports a dataset. Another common form of data you'll see within the repository is time series. As I just mentioned, one way of representing data that we've seen a little bit in some previous lessons but haven't really discussed yet is how to use time series. These are a way of representing time-dependent data, like, for example, our output from audio local measurements, where the timescale is the duration of the audio file. Time series have a set of properties that we can access. The syntax will look somewhat similar to how we use functions, where we have the time series where we would have the function name, and the property where we would have the function arguments. We can see all possible properties by calling the property properties. If we want to get at the raw numbers being used, we can use the properties times and values. We're using the function thread to group together each time with its corresponding value. Some of our basic statistic functions will work directly on a time series without us needing to get all of the times and values ourselves. For example, we can put a time series right into the function mean, and also into some of our plotting functions like list-line-plot. If we want to edit or change our time series, we have specific functions to do that. If we wanted to shift the times within the series, the function timeSeriesShift takes in a time series and the amount of time we would like to shift it by. The output is another time series, so it's a little hard to see the difference at first. If we plot both our original series and the shifted series, we can see how all of the values have been moved. If we want to add in a point into our time series, it's easy to do that with the function timeSeriesInsert. Let's add in 2 new points. So we'll have each point as a list of the time and its corresponding value, and then we can put that into timeSeriesInsert with our original time series. Again, we can see how those have been added in if we plot both our starting time series and our time series with those additional points. Moving on from time series and more into generally working with data, just like how we use time series within a list plot and with mean, those same types of functions also work directly on lists of data. So if we use table to create some data, we can easily pop that list into list plot and into mean. List plot is helpful for getting a visual sense of data, but beyond that, we may want a more rigorous representation of it with a fitted model. There's a few different approaches we can take, and it'll depend on the type of model we're trying to fit for. Since we made this data ourselves, we know that it should fit the equation x plus 1 squared. However, sometimes we might just be looking visually at first for what form of equation is going to fit our data. We can use that info with the functions fit and nonlinear fit to get a fitted model. Fit takes the data as the first argument, and the second argument is the general form of the model, and the third argument is the variables we're using in that general formula. If we want to try to fit an equation with the form of some constant times x squared, our second argument is just x squared. We assume every item in the formula is going to be multiplied by a constant. So if we wanted to have it in the form of c, some constant, plus a, another constant, times x squared, we would have to add a 1 to the list for our second argument. For the function nonlinear fit, it's a similar concept but a slightly different syntax. Again, our first argument is the data. The second is still the form for the model, but we explicitly write out an equation with those constants and variables instead of just assuming those constants are already there. Our third argument is a list of the constants, and then our final argument is the variables. Now that we have the models, we can use them and fit them. The output of fit is already structured as an expression in terms of x, so we can put that into something like plot directly. Nonlinear fit, however, returns an object that we call a fitted model. To use a fitted model in a plot, we need to treat it like a proper function. This means in order to make sure plot knows we want to be subbing in x for the variable inside a fitted model, we need to call it like a function with square brackets and an argument x. This chapter is really only getting started on all of the functionality for data analysis in Wolfram Language. If you're looking for further resources, check out the links in the Going Further section of the lesson notes. What you now have are the skills to get data into your notebook in a variety of ways. You know how to work with a time series as its own data type, and you've seen some basics for statistical analysis, including fitting models to data.
All right, awesome. Let's go on and do, I believe we have one poll for this section. All right, awesome. Cool. It looks like the majority of y'all got it. A little bit of confusion there. But the correct answer is D, which is the last one that you guys can hopefully see right now. So we want to make sure that we remember that if we're getting the properties of something, we're usually using single square brackets. And if we're trying to get the parts of a list, we're going to use double square brackets. All right, awesome. So let's move on to our exercise for this section. So our first exercise, we're going to build a time series. So we want to take the data set Mr. Rogers sweater colors from the data repository and turn it into a time series. And we've got some extra info here that it's going to import as a data set, which is what this little table looking thing is. And then to make it into a list, we can use the function normal. And to get our pairs set up, we can look at thread or transpose. So great, we've got some little hints to get started up here. I've gone ahead and I've already gotten the data set into my notebook just because it sometimes takes a little bit of time to load and get it from the repository for the first time. Great, so we've got this data set, and I'm going to, let's do sweater list. I'm going to use normal on my data set, which is sweaters, and I'm going to suppress that out because it's a very, very big list, but then I'll show you a couple of the entries in it so we can see what we're working with. So using normal has changed this from a data set to a list of associations. and each one has these 3 different columns: episode number, date, and sweater color. Episode number, date, sweater color. Great. So now we know we want to get to make a time series. We need to have a list where we have pairs of dates and whatever value we're working with. So in this case, it's going to be the color here. So let's first get the dates, and we can do this with list manipulation. So we can take our list of all of our dates, and I'm going to use part, and I want to say from all of them, I want to get, and there's 2 different ways you could do this. You could use 2. It's going to get the second thing from that association. So let me show you the first entry here now. So we've got 1 date. We could also write date here, and it's going to give us the exact same thing. So either of those work fine in this instance. We're also going to get the colors. And again, just list manipulation stuff. So we can just put either 3, or we can put sweater color here. And we want to make sure whatever this says matches whatever key we're trying to get from our association. So if I run this, and then I'm going to come down here and just show you that first color, which is yellow. So this makes sense. We've got our first date, which is this date here. And we've got our first color, which is yellow. So now that we've got a list of dates and we've got a list of colors, we can combine those using thread. So we can do dates, colors, and then this will give us, again, going to suppress this output because it's a big old list. And I'm going to do time series data. And just show you the first couple there again. So we've done thread. We give it a list of our list of dates and our list of colors. And it goes through, and we now have these lovely pairs. So now that we have a list of the pairs, we can just do time series of our time series data, and it'll give us a lovely little time series. So we've built one. A lot of times when we're working with time series, the early stuff is mostly list manipulation. And then we get into the fun things we can do with time series, which is what the rest of these exercises would be about, that you can go work on your own. All right, awesome. I believe with that, we're going to move on to the next video, and I'm going to pass things off for the exercise portions to Rory.
Fantastic. Thank you so much. So yeah, we're going to move on to do the first video of the next section, which is on video game development. So these 3 videos that we've just watched are all about sound, and so now you can go and do the sound project, which is super fun, doing some nice visualization of sound. And then, so that we don't have to do lots of videos tomorrow, we're going to do this first video of the video game development section today. So the kind of big goal of this first video, and then the videos that we'll show tomorrow, is that you'll then be able to write 2 different video games, a text-based video game and a graphics-based video game. So the text-based game is going to be like a choose-your-own-adventure game, and the graphics one is going to be a Pac-Man mimic. And yeah, so let's start off with our first video, and we're going to learn about conditionals and writing your own functions.
Hello, and welcome to the final section of this course, where we're going to be focusing on game development. So before we get into games, we're going to have to learn some more content. So in this lesson, we're going to be focusing on conditionals and writing your own functions. So the learning objectives for this lesson are that we're going to be able to construct code using if and which. We're going to be able to contrast equal with same as, and we're going to be able to recognize and or, and we're going to be able to define functions with input restrictions. So we've got a lot of content to cover in this lesson. So the first thing we're going to look at is the function if. Function if takes something and tests it against a pattern that we give it. If the test is true, then it puts out the first output that we specify. If the test is false, then it does something else. We think about if as having 3 parts. A test, something to return if the test is true, something to return if the test is false. We call this if test then else. So if test is true, do this, else do this. Let's look at an example. We can use the same pattern as we used for match Q earlier. So our test is, will the match Q of these 2 things give me true or false? If it's true, then do this. If it's false, then do this. So we're going to say, does match Q of hello and hello give us true? If it gives us true, then return they are the same. If it gives false, then return they are not the same. These two things are the same, so we're going to get they're the same. If we try something a little bit trickier, so we say match Q of these two things, which are both blue, but presented in different ways. It's going to give us both blue, because that's what we asked it to do if the test was true. If we give it two things that are definitely different, blue and red, it's going to return that that's false, and then the if statement will return that these are not both blue. So now let's look at equal and same as. So equal and same as, which we represent equal with two equal signs and same as with three equal signs, are slightly different. Equal checks whether two things are equal, meaning they're the same when we run or evaluate the code. For example, 5 and 5.0 are equal because they both evaluate the same thing. So our test is 5.0 equal to 5 returns true. The function same as, which is written with three equal signs instead of two equal signs, is testing to see if the things are identical, meaning that the two things must both be equal and have an identical head. If we test 5 and 5.0 with three equal signs to test with same as, we're going to get false because they don't have the same head. 5.0 has a head of real and 5 has a head of integer. Just like match Q, same as has a Q function, which is testing to see if something is true. This is called same Q, and it's written the exact same way as match Q and does the same thing as triple equals. For example, same Q of 5.0 and 5 is going to give us false. We can also test multiple things at the same time using and or. So let's look at and. We can use the function and, which we write with two ampersands, to say that we want this subtest to be true and this subtest to be true in order for the test to tell us it's true. So let's give it a try. In this if statement, we're going to have two match Q statements, asking if the thing is a string that says hello, and we're going to be asking if the thing has a head of string. If both of the match Q statements are true, this one is true and this one is true, we're going to return it's a string that says hello. If one or both of them are false, we're going to return it's not a string or it doesn't say hello. Perfect. The second function we're going to look at here is OR, which we represent with two vertical bars. We use OR when we only need one of the subtests to be true in order for the whole test to be true. So let's try testing if this string is a string that says hello, or if this thing is an item with a head string. If either one of those or both of those is true, it's going to return the true statement, and if both of them are false, it'll return the false statement. So again, let's try if something is totally different. So let's run through a string that says bye. So the first test is false, but the second test is true because it has a head of string. So in this case, we're going to pass it as true, and we're going to return it's a string or it says hello. If it's something totally different, we're going to give it the color blue, then it's not a string that says hello, and it's not something with a head of string. So both of them are false, so now we're going to run through our false statement. Great, so now we're going to look at the function which. Which is a little bit more complicated but it's also much more useful. Which can perform multiple tests, which we're starting to do with if, but it can also give us a different output depending on the outcome of each test. So the structure of which is that the function is which, and then the inputs are test1, and then what happens if test1 is true, and then test2, what happens if test2 is true, etc. So let's run this through. If we say x is 5, and then the first test that we're going to run is x a string? If that's true, we're going to return string. If it's not true, then we're going to move on to the next test. Is x smaller than 10? If that's true, then we're going to return number smaller than 10. And for right now, we're going to leave it at that. So if I run that with x is 5, I get a number smaller than 10 because that was the first test that gave it true. What if my x is not a string and it's not smaller than 10 in this which statement? So if we set x to be 50 and then we say, is it a string? Nope, so I'm going to skip that. Is it smaller than 10? No, so I'm going to skip that. Nothing happens at all. If we don't care, then we can just do a catch-all default return at the end using the function true. So we've added at the end the function true. True will always return true, and so if it's true, then we return shrug, and that's fine. If we do care, then we can add infinite tests into the which statement. So let's try a different which. If the thing is a string, I want to be told that it's a string. If it's an integer, I want to be told that it's an integer. If it's a 5, I want to be told that it's a 5. So let's set x to be 3, and then let's do our test. So string q, not a string. We're going to skip that one. Is it an integer? Yes, it is an integer. So we're going to get integer. So great. My which tells me that 3 is an integer, and it would tell me that hello is a string. But what happens if we run it with 5? So if you run it with 5, it returns integer. And what I actually want it to return is, it's a 5. So that didn't work. Which does the tests in order that you put them in, and it stops the first time that it reads true. It tested to see if 5 was a string, got a false, then it tested to see if 5 was an integer, got a true, and returned that. So your more specific things need to be at the start of the which statement. So let's rearrange that which statement so that we start with the most specific thing right at the front, and then we go more general, and then we end with a really general statement, which is just our default. If it was none of the things that we tested for, then it must be true, and then we'll give it a shrug. So we can see now with x is 5, it's going to give us it's a 5. If we set x to be blue, it's going to give us a shrug because it didn't come up with any tests before it got to true. And if we set x to hello, it'll tell us it's a string. So, next section is specifying function input. So we learned in the variables and functions section how to write a basic function. We do that with specifying the function name, giving it what we're going to call our input, doing a set delay, and then doing something with our input after the set delay. Now that we have some more coding skills, we can get more complicated with our functions as well. So for example, we can specify what type of data the function will work with. So let's make a function that takes a real number and turns it into a color. We can do that operation with a function called hue. So hue of 0.4 gives us this nice little green color. So let's make a function, we'll call it style function, and it's only going to take real numbers. So I need to specify that the head of my x needs to be real. Then we're going to set delay that and call it hue of x, and that's what we'll return. So now when we run this function using a real number, it turns the number into a hue. If I put a string through the function, things start to get a little weird. So I haven't told it what to do with a string, so it will just return string function of hello. Our function looks at the head of the variable, sees that it's not a real, so it doesn't do anything. We can tell our function to do something different with string by just defining the function again. So we're just defining it twice. So let's have, if we get a string, we'll just have it print the string in a random color. So style function, when x is string, is going to set delay to style of x goes to a random color. Now let's run style function hello, and now it's just going to do a nice random color for us, and it'll be different each time. Nice. Now we can use map to do the function to a list of real and string variables and do a different thing to each type of variables. So let's just make a little data set with some random real numbers and some random words. So I'm just going to call my data set, and I'm just going to riffle my random numbers and my random words into a nice little data set. And then we can do our function to each of them using map. And now our nice little function does a different thing depending on the head of the item that we're passing through it. So in this lesson, we've covered conditionals and writing your own function with very specific inputs. And our key takeaways from this lesson are that if we want to only run code if it passes a test, we can use if or which. If works best if we have one test, and which works best if we have multiple tests. We can use equal and same as part of tests. Both of these will test if two items have the same value, but same as will also check that two items have the same head. And or let us build more complex tests by combining them together. We can write a function with an if or a which statement in the code. We can also specify input requirements within our function definition. Great, well done. That was a lot of content. I hope you enjoyed it, and we will see you in the next lesson.
Fantastic, great. So we're not going to do a poll for this section. We're going to skip straight through to our exercises. So let's grab up a screen right here. So we're going to do exercise 3 and 4 for this. So exercise 3 is we're going to write a function that returns yes if the input is a string and returns no if the input is an integer, and we want to use a conditional for that. So let's just think about what our conditional might end up being for that. So we're going to want probably a which statement, and we're going to want to test if it's a string, so we can use our string q function, and we want to test the thing. And it looks like we want to return yes if the input is a string. And then we can use our integer q function for our thing, and we're going to want to return no if that's true. So we're going to want to make our little function for this. So let's call it our yes no function, and we're going to want, let's just call it our input. So we want a little input, we want to do our set delay, and then we want to put input into our slots. And so then if we run that, then now we have our little function, and let's test it with, let's have a string here first. This is a string, and it's going to return yes, because that's what we asked. And if we do an integer, let's have 8, it's a good number, it's going to give us no, which is also what we asked. So nice. So we managed to write a little function, it has a which statement, uses our conditionals, returns something different depending on its depending on the input that we put in. So let's do number 4 as well. So we're going to write a function that returns yes if the input is a string and no if the input is an integer, and this time we're not allowed to use conditionals. So in this case, I guess we'd want to define our function twice. So let's have a new function name. Let's call it a string int function. And the first one, we want to see if it's a string. So we're going to do input of type string. And if it's a type string, we just want to return yes. Fantastic. And we're going to want to make a separate definition, and let's spell string correctly. How about that? String int function, string int function. And this time, if our input is an integer, then we want to return no. So now we have our string int function, and if I try it with hello, I'm going to get yes. Fantastic. And if I try it with 8, I'm going to get no. Amazing. Okay, so we've learned 2 different ways of, using conditionals and of defining functions in more and more complex ways, which is going to be super helpful as we continue to move through this course, and really helpful as we continue on our Wolfram language journey. So fantastic. So what we want to do now is you should go and do the exercises and quizzes for the sound functions section, and feel free to try and do that project as well, the sound visualization project. That's pretty fun. And you can start doing the exercises as well for this first section of the video game development section, and feel free to have a look at the projects for that, and see if you can get started on those yet. But we haven't covered a lot of the content that you need in order to do those, so don't worry about it.